Irrational numbers are famously uncooperative. They never repeat, they never end, and they refuse to be written as simple fractions. So you might think that taking an irrational number to an irrational power would only lead to more chaos. But what if I told you that two irrationals could perfectly align to produce something rational? Here's the puzzle. Can you prove that there exist two irrational numbers, p and q, such that p to the power of q is actually a rational number? It feels like we should have to search through a vast forest of numbers to find them. But surprisingly, we only need one clever example to prove they exist, even if we don't know exactly which pair it is. Let's start with the most famous irrational number of all, the square root of 2. We'll consider a specific candidate for our proof, the square root of 2 raised to the power of the square root of 2. Now, we don't know right away if this number is rational or irrational, and that's perfectly fine. We'll just look at both possibilities. First, let's look at the simple case. If the square root of 2 to the power of the square root of 2 is rational, then we're finished. Both our base and our exponent are irrational, and their power is rational. We found our pair. But what if it's not rational? What if this number is still irrational? This is where it gets elegant. If our first number is irrational, we'll use it as the base for a second calculation. We take this entire number, the square root of 2 to the power of the square root of 2, and raise it to the square root of 2 once more. Now, by the laws of exponents, we just multiply the powers together. Root 2 times root 2 is just 2. And there it is. The square root of 2 squared is exactly 2. This means we've taken an irrational base, our first number, raised it to an irrational power, root 2, and the result is the perfectly rational number, 2. No matter which case is true, we've proven that such a pair must exist. This is a classic example of a non-constructive proof. We've proven that the pair exists without actually knowing which pair it is. It's a beautiful moment in math where logic alone bridges the gap between the irrational and the rational. Thanks for watching, and stay curious.